Hi everyone, Jake the Foxy here, back in Plasma once again to bring you yet another invention. Now, I've already tried making a car of my own design, as well as a roulette wheel. So for my third project, I decided to try and make a Rubik's Cube inside of Plasma. Now, how well does a Rubik's Cube actually translate into Plasma? Well, I'll let you guys be the judge of that. So then, the primary way with which you can control the Rubik's Cube is with this device resting on the table right here. All you have to do is fly right up to it and press the F key, and it will automatically mount on the side of your little robot drone player character. And if you press the B button, you'll notice that the menu at the bottom of the screen now changed to the controls for the Rubik's Cube. And I will be explaining each of these in turn, so if you want to download this world and try playing out with the cubes yourself, you can. Now, the first thing to notice is that the scroll wheel will cycle through each of the different sides, going from red to blue, to green, to orange, to yellow, to white, and then back to red again. And it can move up and down through all the sides to select the side that you want. And an important thing to note here is that instead of the sides being denoted front, back, left, right, like they usually are, here I decided to go with naming each of the sides after the center square of the side, which never changes. This means that you can always uniquely identify the side by the color of its center square. This is true for any Rubik's Cube. And I really wanted to do it this way because otherwise, whatever side's the front could be changing depending on how you're looking at it. But with this way, it's completely unambiguous. Now then, if you notice, when I click the left mouse button, the side I have selected rotates counterclockwise. Conversely, if I click the right mouse button, it will rotate clockwise. And if I select a different side, then that side will rotate when I click the mouse buttons. And this is basically how you control the cube and try to solve it. You'll also notice that the counter on the device has been going up every time I make a move. So this way you can keep track of the number of moves you've made if you want to try to challenge yourself and solve the cube in the fewest number of moves possible. If I press the 1 on the keyboard, the cube will reset back to its default state, and the counter will reset back to 0. Of course, trying to solve a cube in its default state when it's already been solved is kind of boring. So you can choose to scramble the cube by pressing the 2 key. And here it will automatically start scrambling the cube for you, which it does by basically doing a bunch of random moves. Well, about 20 of them, I think. Now, sometimes it will make a move that undoes the previous move, but this doesn't really matter because in the long run of things, it winds up getting pretty well scrambled anyway. And if you're still not satisfied with the scramble that you get, you can just do it again to do it some more. And it'll just keep going. Now, notice that while it's scrambling, as well as while it's rotating, the LED on the controller has turned red. This means that I can no longer interface with the cube. Instead, I have to wait for it to finish scrambling. I can still change which side I have selected because I'm not actually controlling the cube in that case. See, now it finished and it turned green again, which means I can now turn the sides of the cube. And the third button on the control, number 3, turns the display on and off. So if you're one of those guys or gals who likes to try to solve the cube blind, you can totally do that here. And or if you just want to scramble the cube without seeing what it's doing, that totally works as well. Of course, you can also just look away, but if it's too much too hard to resist, you can just turn the display off. Also notice that the counter resets with each scramble as well, so that's yet another way to reset the counter. And then when it's done scrambling, just turn the display back on. So that's basically how the cube works, if all you're interested in is playing around with it and attempting to solve it. But what if you actually want to tinker with it and see how it functions? Unfortunately, you can't just press Q like you normally would to open the sketch. If you do, you'll get a message saying that there is more than one controller on this device. And if you thought a Rubik's Cube ought to be simple enough to only need a single controller, oh, you sweet summer child. But anyway, you might have noticed a not-so-secret button on the side of one of the faces. And if you press that button, it'll open a secret compartment that will allow you to access the interior of the cube where all the controls are stored. Now notice that each of the sides has its own dedicated controller, and each of them are color-coded just to keep it well organized so you can easily tell which controller is controlling which side. Also, each side has its own servo, which is also color-coded, which controls the rotation for that side. In the front, you can see the transceiver here, which is responsible for receiving the signals and commands from the remote to allow the player to actually control the cube. There's also a speaker here, which plays the beeps and boops that you hear when rotating the various sides, as well as a small fanfare when you actually complete the cube. But the main controller for orchestrating this entire thing and interfacing with the other subcontrollers is this one right here, this black one. So why don't we check out the sketch and dive right in. Now, I know this might look a little bit intimidating, but I'll do my best to give you a brief overview so you can more or less understand what is going on here. And it all starts right up here in this section with this main control Lua program. And if you'll notice, I have a singular Lua program node, which basically functions as the brains of the entire cube, if you will. So whenever you send a command to the cube, like say to rotate aside, that is picked up by the transceiver, which is then turned into an actual function call, which is then called within the Lua program. And if we take a peek at the source code here, you can see that each of the different sides has its own rotate function. Now, I possibly could have combined all of these into a single function, but that function would have been very complex, and I found it easier just to do it this way. But the main thing to notice here is that all of these rotate functions, they all end with a call to this getRows event. And the reason for that is because when you are rotating one of the sides, you need to know what state the cube was in before the rotation. And with the way I've set things up here, the state is basically distributed among all the different sides. So the getRows event allows us to retrieve that information. And if we look over here, we can see this is where the getRows event is actually processed. And it basically just feeds straight through into this huge section over here. Now this section might be the most intimidating because of this huge mess of wires leading everywhere, but this is basically all just assuring that all the information goes to where it needs to go, and it all makes sense, I promise. Now, this huge column of components going right down the center here, these are all the different controllers for each of the sides. The blue part is the main interface that you get with every controller within Sketch, while the pink part is a custom module interface that I designed for being able to control each of the sides. How it actually works isn't all that important right now, because we'll get into that in more detail later. Just notice that the getRows event is fed into each of the module interfaces, triggering the getRow event within that module. And when the getRow event completes, it sends out the data that we requested on this row out output, which then comes around and is written to these various different variables with this bank of variable writers, because we have to store the data somewhere. And I actually use a lot of different variables in this sketch to try and cut down on the number of wires that I need. But as you can see, there's still quite a lot of wires. But anyway, as soon as it finishes writing out all of the output, it then triggers yet another event titled row ready. And if we swing back around now to the main Lua program, we can see that the row ready event actually winds up calling yet another function within our Lua program titled row finished. And if we jump back into the source code now and scroll a bit further down, you can see a few more helper methods, and then we can see the finish rotation function. Sorry, this is the function that was actually called. But basically what this function does is that it reads the data that we just collected that was written to those variables, and then it writes that data back out to each of the different sets to determine where the data ought to go to with this write variable array function, which sounds really confusing, but trust me, I hope it'll all make sense in the end. We also set a couple other variables just to note which way we're actually rotating and which face is being rotated. And then we send all of this data out by calling send push data. And that triggers yet another event with the name of push data. And if we come down all the way here, we can see where the push data event is processed. And this section here might look odd, but basically the reason for this is because at this point in time, Sketch doesn't really support multiple nested arrays, and unfortunately the best way to represent the data of the Rubik's Cube is with a nested array. So the way we work around this is that we actually construct the nested array as a numeric array that we treat as text, and then we put that in a text array. And we built that up in the code back in the Lua program. And this section right here is basically just undoing all of that in Sketch so we can actually write out the data to each of the different sides that need it. And that's what all these pink lines are mapping right here. Writing out that data to the toPush variable, which will then be used when we call the pushRow event. But also coming back over here, notice that when this thing finally finishes through, when it's done enumerating through our array, it then calls yet another event. This is the third event now we've called to do a single rotation called rotate. And now that we've already collected all of the data that we need and sent the data to where it needs to go, now we are finally ready to perform the actual rotation. So, if you think about it, whenever you turn one of the sides of the cube, you're not only just affecting that side, but you're also changing the state of each of the 4 adjacent sides. So because of that, whenever we perform a rotation, we need to update not just the side that's rotating, but also the adjacent sides as well. And that's basically what this rotate event handler is doing. It maps this event to each of the different sides that needs updating. And it does that by triggering the rotate command on the controller for the side that's actually rotating, as well as triggering the pushRow command on all of the adjacent sides to indicate that, hey, this side needs to update its data as well, which is why we had to fetch the data that we were going to push to that side before calling that event. Now, as soon as the main side finishes rotating, it indicates that by triggering this end rotation output right here, which allows us in turn to trigger our own end rotation event. And that basically allows us to do a couple different things, like inform the user that, hey, this rotation has finished, you can do more stuff with the cube now. But in addition to that, at the end of every rotation, we also check to see if each of the different sides of the cube is in a solved state or not. And if all the sides are in a solved state, then we know that the cube itself has been solved. And at that point, we can go on and trigger the win event. Now this just leaves a couple more sections that we still need to cover, like this speaker output section, which basically, as its name suggests, controls the speaker. It's responsible for playing all those different beeps and boops that you can hear whenever you perform a rotation. And it's fairly straightforward, so I don't need to go into any in-depth explanation of that. And down here we have a similar section, except this one is responsible for toggling the display on and off. Again, it's fairly straightforward, so no need to go in depth. And down here we just have this small section is where I tossed in a couple of extra features that needed to be read and sent to the transceiver, which I just didn't have room to fit in anywhere else, so I wound up sticking them here. And we have this section as well, which doesn't pertain to the cube itself per se, but this just allows us to push the button to open the front panel, which is how we access this sketch in the first place. And that finally leaves this section up here, which might look a little bit more complex, but basically all that this section does is that it causes the cube to play a fanfare and to blink on and off when it detects that the cube has been solved. And I just wanted to add that in because I felt like the cube needed to do something when the player solved it, as opposed to just sitting there. And that basically covers the entire sketch for the main control. Next, I'll be moving on to each of the individual side controls and showing you how the sketch operates there. Now, I'm only going to show you one of the side controllers because all of the others are more or less identical, and once you know how one of them works, you know how they all work. And once again, I have this central control region which contains a single Lua program node, which basically serves as the programming for this particular side of the cube. Now, if I look at the interface section over here, you can see I have commands, properties, and outputs, and this is what basically defines the custom module interface that I showed you in the previous sketch. And most of the different properties correspond directly with input variables to the Lua program. Each of the different commands tends to correspond with a different function that we can actually invoke within the Lua program. And likewise, many of the outputs are output directly from the Lua program. So let's go ahead and take a peek at the source code. Now, as you can see here, I have a few different internal functions just to help me out with different methods, but including this update display function here. Now, internally, the display is stored as a 3x3 matrix, but this converts it into a single one-dimensional array and then outputs that array on line 1. If we follow output 1, we can see it leads over here to this display control section, which looks pretty involved, but basically what it's doing is it's iterating through that array that we just sent over here, and inside the array, instead of storing the actual color values, we're storing an index into a palette, which is being selected for here, where you can see the individual colors of the Rubik's Cube: yellow, orange, green, blue, red, and white. And so that gets forwarded on through these mappers to target the individual LEDs. So each LED corresponds to a different element in the array. And I also have a few extra nodes over here for changing properties that don't really need any sort of Lua code, like turning the display on and off or setting the delay. So I just put these over here because there was some empty space. So moving back to the Lua program, we can check out the rest of the code. The next function up is the push function, which is what actually takes care of updating the internal state for this side of the cube. It doesn't actually update the display, though. That's handled in the function that we just saw. And then we also have this other function here for checking to see if this side of the cube has been solved. And then we come to the external functions, which are functions that are actually called from the outside. The first of which is initialize. As the name suggests, this sets the default initial state for this side of the cube. This function also gets called whenever the cube is reset. So if you are wondering how the reset function works, this is how. And then next after that, we have the getRow function. Now, if you'll remember from when we were covering the main control, we had to use this in order to get the state out of each of the individual sides in order to tell the other sides how they should update. So basically, this first looks at which side we are addressing. And now here, side does not mean which side of the cube, meaning which face, but rather which side of the face itself. So the side of the side, if you will. Like, do we want the top row or the bottom row or the left column or the right column? It's definitely confusing, but unfortunately this is just the way it has to be. And then it takes that data and outputs it as an array so that the main controller can then read it and send that data to where it needs to be. Once it does that, though, we are ready to actually update the data in the side controller, which is what the push row is used for, which starts the whole process by triggering the animation sequence on output 4. Now, if we follow output 4, we can see that it broadcasts a push row event. And now the push row event, if we come down over here, we can see that it actually triggers yet another function to be called within the Lua program, called advance. Not only that, but it triggers this function 3 separate times at different time intervals. Now, why would we do it that way? Well, I don't know if you noticed in the previous segments, but whenever one of the sides of the cube rotates, the other adjacent sides do not update all at once automatically. Instead, we only update one cell at a time. That way, this gives the illusion that the adjacent sides are actually rotating along with the dominant side, even though they are perfectly stationary. I thought it was a pretty cool effect, but it was an absolute pain to try to implement, as you can clearly see. But anyway, here is the advance function, which basically handles the animation. It calls the push function, which we just saw, to update the state one cell at a time, and updates a counter variable, and updates the display so we can actually see it animating. Once that count goes above 3, we know that we're done with the animation because there's only ever 3 cells to any one side or row, so we can just reset the count and check to see if the cube has been solved at this point. Now, that's basically how we handle updating the adjacent sides of the cube when one of the sides rotates. But to handle the rotating of a side itself, we use the rotate function, which first checks to see if we're already rotating, because, as I mentioned earlier, it can sometimes mess up the state of the internal state of the cube if you try to do too many rotations in a row. So you really need to wait until the side finishes rotating before you do another rotation, and this just helps us to enforce that. And basically we just check to see if we're rotating clockwise or counterclockwise. We set up the relevant sides for that rotation, and then we indicate either a clockwise rotation or a counterclockwise rotation on output number 5. And if we go to see what output number 5 does, it actually broadcasts another event for us called rotate event. And that is actually handled down here in the servo control section. Now, because we're doing this animation, we want the rotation of the side to sync up with the animation of the adjacent sides. So we can't just set the target rotation for the servo and forget it. We need much finer grain control for that. So we use this math expression node here to calculate how long the rotation should actually take. And then we use this number tweener to control the target rotation of the servo at each individual tick so that it continues to rotate smoothly and reaches the final target rotation at the same time that the animation finishes. And that's a lot, but I hope that that makes sense. And when it's all done with the rotating and animating, it updates a couple of internal variables, which just helps us keep track of things, as well as signaling the end of the rotation by triggering the end rotation output. And that's basically the entire sketch for the side controller. Now, I hope all that made sense, but maybe it would be a bit easier to understand if I actually showed a demonstration of how the individual sides work. So why don't we do that now? So this is a test build that I created while I was prototyping the various faces that would later be assembled into a complete cube. Now, please ignore any spelling mistakes, but this control panel right here basically allows us to control the active face in much the same way that the cube itself would internally. For instance, we have this switch right here that allows us to toggle between clockwise and counterclockwise operations. We also have this dial right here, which allows us to select between the top row, the right column, the bottom row, and the left column, which we collectively call rows for simplicity. We also have this set of dials right here, which basically allow us to select any of the colors of the cube. And notice as I change the colors here, it changes this row of LEDs. And we basically use this to select the data that we will push into this side of the cube. And we need this because normally this data would come from some other side of the cube, but because we're only working with a single face, we have to input this data ourselves. So, when I press this button, labeled push, you can see it pushes the data that we selected onto the active face. And if I reverse the direction and press the push button again, notice that it pushes the data the opposite way. Similarly, if I change the selected row from top to, say, right, and press push again, it now pushes the data on the right side. Now, we also have these two triangular buttons down here, which allow us to rotate the active face, both clockwise and counterclockwise. Now, notice that I still have the right side selected, but the face is no longer in the same orientation that it was in before. So what do you think will happen when I press the push button now? It pushes the data onto the right side of the face, just like we selected. That means that the right side always refers to the side that's on the right, irregardless of the orientation of the face. And that's important because when we're rotating the various faces of the cube, we want to push the data onto the sides that are adjacent to that face. And we don't want to keep track of which side is the top and which one is the right. We want to handle all of that internally in the faces controller, so there's less work for the cube itself to do. Now, we also have this button down here, which allows us to read data from the active face, such that if I push this button, notice that we read the data from the right column. Pink, blue, green. Pink, blue, green. Now, if I reverse direction and press the button again, okay. That's a glitch that can sometimes happen with this prototype right here. But that is definitely fixed in the cube itself, so you don't need to worry about that. Now if I try that again, there we go. Now it's reading in the opposite direction. So the way that you read the data also depends on whether you're in clockwise or counterclockwise mode. Similarly, I can rotate the cube again, and if I try reading again, then I'll read from that column instead. If I try selecting the top, which is green, blue, green, and try reading that, we get green, blue, green. Now, finally, if I turn all of these back to yellow, like so, and rotate it one more time, I can push that data in. Oh, I'm still on the top. I meant to be on the right. Push that data in, and then rotate some more, and just clear out the cube, like so. Then these lamps will turn on up top to indicate that this face of the cube has been solved. So now that you hopefully understand a bit better how the cube works internally, let's see if I can actually solve this thing. So, I now have this fully scrambled cube right here. So, why don't we see if we cannot solve it? And there you have it. Now, I must confess that I did not actually solve that scramble myself. I actually used another program outside of Plasma to solve the scramble for me. But at least this does show that my cube that I built here actually works, which is all that I wanted to show with this demonstration. Now, I would love it if I could somehow program the cube inside Plasma to automatically solve itself, but this project has already been daunting enough as it is, so that's something that I will have to save for a version 2, which I will definitely post a video on if and when I ever get around to it. But I also have a whole bunch of other ideas for devices and things that I want to build in Plasma. So if that's something that you're interested in, please make sure you subscribe. And with that, I'll see you guys next time. Bye!